Hello Math 3 to 11 students. Let's begin lesson 14, quadratic reciprocity. Lesson 14 is a continuation from lesson 13, quadratic residue. So we begin with section 3. By the way, I covered a part of section 3 in lesson 13 as optional topics. I think I left 2 videos there. If you went through those and if you feel comfortable, you can skip the first half of section 3, about 2 videos. Otherwise, let's begin. Let P be an odd prime and let P does not divide A. In other words, A is non-zero modulo P. We define the Legendre symbol A over B defined like this. Positive 1 if A is a quadratic residue of P. Negative 1 otherwise. We use not only the abuse of notation expressed exactly like a fraction, but also we abuse the terminologies as well. We call A and P as the numerator and the denominator of the Legendre symbol. Even though this is not a fraction, I'm going to use the term A over B or 5/17, things like that. So it may get a little bit confusing if you just trust what you hear. So don't trust what you hear, trust what you read. By the way, positive 1 if quadratic residue, negative 1 non-residue. Haven't you seen this before? You must have. It's the precise replica of Euler's criterion. A is non-zero mod P, then A to the P minus 1 over 2 power is congruent to 1 mod P if and only if A is a quadratic residue. Moreover, if it is positive 1, then quadratic residue, negative 1, then quadratic non-residue, otherwise 0 and nothing else. By the way, this A is 0, that's just a singular case, and we end up with equal number of all those. So P minus 1 over 2 quadratic residues and P minus 1 over 2 non-residues, and then 0, so they all add up to P. So you can consider this symbol as a shorthand of A to the P minus 1 over 2 power. And if you feel a little bit more comfortable with Euler's expression, Euler's computation of A to the P minus 1 over 2 power, you can go ahead and use that. But most people find it more convenient to use a little bit more simplified symbol. And in some cases, such small simplification work wonders and make really complicated computation into something much more manageable. For that purpose, let's go ahead with some properties of Legendre symbol. And among those, the most important is this one here. Let's begin from the top. If A and B are relatively prime, what am I talking? Sorry about that. If A and B are congruent modulo P, then A over P and B over P are the same. So they are both positive 1 or both negative 1 because A is a quadratic residue if and only if B is. A squared over P is always 1 because square number is always a quadratic residue. If you put x as A, then x squared is A squared. And then this one here, yes, we talked about it already, just Euler's criterion. A over P is congruent to A to the P minus 1 over 2 power. And we are assuming A and B are non-zero mod P, by the way, so we don't have to worry about the singular case becoming 0. Finally, this one here. This one requires a bit of a dirty work. We have to consider all cases, A and B, and for each, plus 1 and minus 1. So we end up with 4 different cases, kind of like a coin tossing. We have head, head, tail, tail, head, tail, and tail, head, basically. And for each, we just manually calculate and see if this multiplicative property actually works out. AB over P is A over P times B over P, like that. Yes, it does work out. So basically 1 times 1 is 1, negative 1 times negative 1 is positive 1, 1 times negative 1 is negative 1. Negative 1 times positive 1 is negative 1, like that. Manually, you can check. And then 1 over p is always 1. That's really simple. 1 squared is 1. Negative 1 over p is negative 1 to the p minus 1 over 2 power. Same as this, except that negative 1 to the p minus 1 over 2 power is either 1 or negative 1. So we don't really need congruence. Just equality will do. But if you want precise proof, there goes. And then I said proofs are left for students, but we actually proved them all, right? So we don't really need it. Alright, we went through the properties of Legendre symbol. Let us go ahead with some example problems. Let's see a couple of computation problems. This one is from our textbook. X squared plus 46 is congruent to 0 modulo 47. Does it have a solution? Equivalently speaking, we can say x squared is congruent to negative 46 modulo 17 after flipping this 46 over to the other side. In short, I'm asking whether negative 46 is a quadratic residue modulo 17 or not. How do I do that? Well, one way to do that is to do this, negative 46 to the 17 minus 1 over 2 power, which is negative 46 to the, let's say, 16 over 2, 8th power, and then find out, and then whether it is congruent to 1 mod 7 or negative 1 mod 7. Well, with calculator you can do it. Without calculator, that's gonna be a bit too much of a work. And let's suppose we are learning how to do this without computer. And what is the motivation for that? The precise technique that we are reducing these so that we can do this computation without calculator, with just, human body and brain. That exact same technique is used to much more humongous problem that even the best computers nowadays cannot handle, into much more reduced form, so that you can use our computers to get it done in reasonable time frames, such as a couple of weeks, kind of like that. So this kind of reduction technique, this is, as a matter of fact, a big part of number theory. So do not just disparage it simply because you can do this kind of computation with calculator easily. What if you have some 100-digit numbers to work with? Somehow you have to reduce it down to 10-digit numbers so that you can do it with computer. It's the very same thing. Okay, alright, how do you do this? One way to do that is to reduce this negative 46 modulo 17, and 51 is 3 times 17, so that's actually 0. So we have 51 minus 46, so 5. So 5 over 17. And then can we reduce it further? Well, 5 is a prime number and already pretty small, so I don't think we can do that. So let's go ahead with Euler's computation. 5 to the 8th power. We already saw that 17 minus 1 over 2 is 8. So 5 to the 8th power, we can reduce it 24 to the 4th power. 25 is 5 squared. And 25 is congruent to 8. 25 minus 17 is 8. And then 8 to the 4th power, we can reduce it to the 64 to the 2nd power. And 64 is actually 68 minus 4, where 68 is 17 times 4. So that's congruent to 0 mod 17. So we get just negative 4 to the 2nd power, which is 16. And that's congruent to negative 1 modulo 17. So this negative 46 is non-residue, so there's no solution. And this is the way our textbook author did the same problem. Is this better? I don't know. And I just did it my way first and then looked up the textbook, and I was a bit surprised. The textbook author did it a little bit differently. Negative 46 over 17 decompose into negative and then 46 and negative 1 to the 17. Well, that turns out to be just 1 because negative 1 to the 8th power, so that's even power. So that drops out, and then we have 46 over 17, and that's congruent to, let's see, 46 and then minus 34, which is congruent to 0 because this is 2 times 17, so it's equivalent to 0. If you do that, you're going to get 12, and 12 can be factorized further, 3 times 4. So we can decompose 317 times 217, and then this one is squared, so it becomes 1. Yeah, anything squared is 1. So we end up with 3 over 17. Well, 3 is a prime number, and then it's small enough, so you cannot simplify this thing any further. Let's go ahead. 3 to the 8th power, so 3 to the 4th power is 81, so 81 to the 2nd power. But 81 is actually 85 minus 4, and 85 is 5 times 17, so that's equivalent to 0. So negative 4 squared is congruent to 16. So that's congruent to negative 1 modulo 17. So that's the computation our textbook author did, compared with the one I did before looking up the textbook solution. I don't know which one do you like better. Me personally, I like the one I did because that's the one I did, but of course, opinions will differ. By the way, in my solution, I think there's an issue here. This decomposition is quite useful, but I didn't use it here in this solution. I came here directly, but here in textbook solution, this 12 decomposed into 3 times 2 squared, so that we get this reduction. And I want to show you an example that you have to do it that way. So I created another problem. So use the prime factorization to determine whether this number is quadratic residue modulo 31. And of course, I didn't ask you to do the prime factorization. I gave you that. So 2 squared times 7 squared times 23 to the 4th power times 19 over 31. How do you work? All the even power actually drop out because we can decompose them all, and then all the squared will go down to 1. So the first reduction is just separating them all and then just throwing away all the even powers. We have basically a bunch of 1s here. So the first reduction yields 19 over 31. That's prime, but too big. So let's do a little bit of simplification. 19 minus 31 is negative 12. And then odd minus odd, we got even. And then we can do factorization. 2 squared times negative 3. So 2 squared, as we saw before, it drops out. And negative 3 over 31. So that's going to be negative 3 to the 31 minus 1 over 2. So 30 over 2, 15th power. And that's negative of that, so negative of 3 to the 15th power. Okay, instead of calculating 3 to the 15th power, let's do this. 27 to the 5th power, yeah, 3 to the 3rd power is 27, and 27 is 31 minus 4. So what do you get? Negative and another negative, 4 to the 5th power, and then 2 squared to the 5th power, 2 to the 5th power to the 2nd power, bingo. 2 to the 5th power is 32. So that's 1 modulo 31. We got the simplification. So this kind of computation can be done much more effectively with Legendre symbol and its algebraic properties. And then we're going to go through even worse examples, some proof problems as well.